function calls itself, you're in a situation that we call recursion. So let's revisit our old friend, the factorial function, shall we? Oh, hi, yeah, you're here. Yeah, you guys can come off. Thank you. So, recall the definition of the factorial function. If you're taking the factorial of 1, or sorry, I always get that mixed up. If you're taking the factorial of 0, that's 1. If you're taking the factorial of any number greater than 0, your definition is it's n times n minus 1 factorial. Notice that factorial is used in the definition of factorial. This makes it a recursive or inductive definition. So it turns out that this actually has a fairly straightforward way of implementing it. There's a fairly straightforward way of going about this in code. In fact, a lot of instances like this, you can sort of almost translate one-to-one from a formula if it's in inductive form like that. Let me just create a new thing. We shall call it first. So if we were to implement this directly in Python, well, first of all, we can call it factorial. It will take some number n. And now we've got a split case going on. This, yes? Oh, yes, excellent, thank you. Yep. Oh, no. No, there we go. Well, that's all the lights. Is that too much? Is that good? Is that better? Okay. Good enough? So, we have two cases here. Your brain at this point in the course should be screaming, this is an else if. We have an if case, and then we have another conditional, so that's an if else if, right? So, if n is equal to 0, we do something. Otherwise, else if n is greater than 0, we do something else. So the question is, what do we do and what is something else? Well, we know that in the case that n is equal to 0, this needs to be 1. So we very simply return 1. In the other case, we have this expression, n times n minus 1 factorial. So, return n multiplied by n minus 1 factorial. As you can see, that's about as direct an implementation of the formula as you're likely to see here. So, let's just let's run this guy. Let's prompt it. Prompt fact 10 executes the entire convection. And there we go. Perhaps one of you can quickly on your calculator verify that the factorial of 10 is 3,628,800. So it's interesting, however, to dig into a little bit of the structure here, what's going on, right? So let's add some print statements. Entering factorial with n is equal to calling back again. So, if we run this again, we can see entering factorial with n equals 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and 0, and then finally, n is 0, returning 1. Now, the interesting thing about this, right? All of these functions, all of these calls to this function are open until after the last print statement here. So, if we were to sort of draw out what's going on here, it would look something like this, right? I'm going to do this two ways. I'm going to do this sort of in a pseudo code like way, and then I'll show you what's going on with the system stack. So we've got a call to function, or a call to factorial, right? At 10. That function call invokes factorial at 9. That invokes factorial at 8, etc., 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 etc. But this does not conclude until, let's just say, factorial of 0. Factorial of 0 will return 1 to the calling function and its execution. So factorial of 1 will receive the return value from factorial 0. It will use that to calculate it for factorial 2, etc., 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 all the way back until the point where the execution defined by factorial 10 receives back the answer from factorial 9. At that point, it returns its final value. Does that make sense? They're nested. All of these things are nested. Yes?
We haven't defined the function completely between inside. So how can we call the function between itself?
We haven't. So the question is, how can we call the function from within itself if it's not defined within itself? And the answer is that it is. The first line here, this guy, that defines the function both for use by other functions and for use by itself. So the function has access to itself within the global namespace. It just does it that way. Question?
Yeah, in recursion, does it matter when you call the function? Like, if you call it
The point, so the question is, does it matter for recursion whether you call it later or earlier? Whether you make the recursive call later or earlier in the execution, or the way that you type out the function. In both cases, the function will still be recursive. If that doesn't break that property of it being recursive. It all depends on how it all depends on how you want the thing to execute. Right? Like, keep in mind, wherever you put that recursive call, the function is going to pause until that calculation is finished before returning to that point. So it's up to you as a designer at what point you want to put the recursive call. But normally there will be some preliminary work. Normally you'll want to break things into cases. The structure of the problem should suggest the structure of the algorithm pretty directly, at least for the easier ones of these cases. Does that make sense?
Yeah, so is it like say that for factorial and you have factorial one more times ago. Say it was actually factorial function or something else, and you called it earlier on, anything after that won't be run.
Yeah, I'll demonstrate for this. I'll demonstrate this for you actually. So let's modify this guy to demonstrate this point a little bit. So Next is equal to m times this guy basically, return next. So print making recursive call, print recursive call finished. Let's see how that works. So you'll notice all of our recursive calls are finishing all at the end of the execution of the program. That's because, as I said, we don't know what the value of next is going to be until the calculation factorial n minus 1 is complete. And that one doesn't know what its value is until it's finished its recursive call, and so on and so on and so on, until you hit the base case. The base case does not require any recursive calls. So once you hit the base case, it can it'll just return a value, which is not dependent on any further function calls, or at least not any recursive function calls. And then that just gets passed back up through the chain. Make sense? Any other questions at the moment? Good questions so far. So this is good. So that's the factorial method of solving the. Sorry, did I say recursive? Did I say factorial method? I meant that's the recursive method of solving the factorial function. So when you look at recursions, this isn't always going to be the case, but it's often going to be the case. Recursive structures tend to have a certain layout. In particular, you most of the time will have a base case, and you will also most of the time have an iterative case. So the base case, that is the one that doesn't make the recursive call. It's called the base case because it just is. It does not rely on anything else. The iterative case, on the other hand, is the one that relies on further information from recursive calls. So that's the one that you have to step into and step into and step into. So this is the implementation in the slides. This is a problem, though. I'm not sure if they discussed this in the slides, but can anybody tell me what the problem would be using an else here instead of actually using the condition n is greater than 0? Yes?
So it says when n equals 0, say return 1.
Mm-hmm.
Else return, so actually it doesn't include any thing about the n itself. It just says else return n times factorial.
Okay, yeah, but like in terms of what physically will go wrong, what will go wrong with that?
Like, so n minus 1, like, is n minus 1 is not defined.
Yeah, you have, just behind you? Yeah, no. You, sir, the answer is on your desk.
If n is negative, it will keep going constant.
Yes, that's the problem. So it's not necessarily a problem of definedness, because by using an else case, n minus, like, all of the negative numbers are included in a case. It's the else case. The else case includes all cases that aren't 0. The problem is, if you start off on a negative number, you're subtracting 1 each time to try to reach 0. If you start off at something that cannot reach 0 by subtraction, you will never reach 0. This is what's known as infinite recursion, and it is a cousin of our much-loved infinite loop. Right? Any questions about that? Yeah.
If you have another elif statement that says factorial n plus 1, then that would cover all cases.
Yeah, but at that point, you're not really defining the factorial anymore, are you? right? You're modifying how, like, what gets calculated. Yeah?
You could just say absolute number.
Yeah, but that's, like, it's not even that simple, right? Because, like, while both of you have suggested things that could fix the problem of the infinite recursion, both of the things you've suggested modify the definition of the factorial function, right? The factorial function is actually not defined for negative numbers, right? So in theory, we don't want this algorithm to work for negative numbers, right? So, in a couple of topics, what we're going to eventually have happen with a function like this is we're going to have to generate something like a domain error or a value error once we learn how to generate our own errors, which is more fun than it sounds like. But yeah, it's like you also have to be careful not to like step outside of the definition of the thing you're trying to implement too far. Make sense? Cool. So, it should be reasonably obvious here which one of these is the base case and which is the iterative case. Hopefully all of you picked up on that. I've already demonstrated this essentially. So, every time we recurse, the interpreter creates a new scope for the variables of the function. So, this gets back into what I was talking about a few lectures ago with the system call stack, right? So, if you imagine the memory space for your execution of programs, like this is like a view into your RAM, right? So, a certain amount of space will be allocated for the main execution. In Python, this is called __main __ because Python loves underscores when it's talking about classes, as we're going to see in about a month. So when we invoke factorial with, say, let's do it simply, let's just say factorial of 4, right? Any of the local variables which are contained in this execution are contained within this stack frame, this segment of memory. When factorial 4 invokes factorial 3, it's allocated a new stack frame. The same variables with the same name are duplicated in the new stack frame. So I think in this one we use next, right? So next exists here. A separate copy of next exists here as well. And so on and so forth for 2, 1, and 0. So, what's very important to understand, the thing that is meant by the word next in any particular context is the next that is in the top of the stack frame. Or, I know in this case it's the bottom, but they often do memory in this, you know, sort of bottom to top. It works, it's fine. Think of it inverted, and everything's fine. This is the top. I know it isn't, but shut up. So, in this particular case, 0 wouldn't have 1, right? Because along the base case branch, we never actually use the next variable. So this stack frame would not have next, but this one does. So, if you were to refer to next, you would be referring to this one. But when these things are deallocated, pop, pop, pop goes the stack. You peel it back and return the return values as you do so, eventually all the way back to main, and that's how the function call stack manages these recursive calls. Now, so the other thing to keep in mind about call stack is that only the top of the stack is ever being executed, like ever being worked on at any particular point in time. If a call for factorial 4 and a call for factorial 3 are both on the call stack, this is the one that it's working on. When it's finished, it'll either call new ones as needed, or when it's finished, it'll pop itself off the stack and give its return value in factorial form. This is how your computer manages function calls. And this isn't a Python thing. This is like a Unix thing, I think, probably. But at any rate. So, let's see here. So you may be saying to yourself, okay, this is fine, but I can't really see how any of this is useful, considering we can do all of this with while loops or for loops and could save ourselves considerable conceptual hassle. What is even the point? To quote a phrase. Well, it turns out that there are certain types of problems which lend themselves naturally to a recursive algorithm. Recursion is a very, very, very powerful technique. Has anybody in the room taken 1JC3? 2 people. 3 people. All right. What's the language they use in 1JC3?
Haskell.
Haskell. What does Haskell use? Yeah, it's a functional programming language. But what does Haskell not have?
No loops.
It has no loops. What does it have instead?
Recursion only.
It has recursion only. So it's actually possible to do anything that you can do with a loop with recursion. But, you know, most people in most languages don't bother. So, certain problems have an inductive structure, right? You're going to see this more and more if you go on to take courses on algorithms and algorithm design. But just as a quick example, there's a thing we have in computing called a binary tree, right? So you may have seen a diagram like this before, but a binary tree is a graph where you have nodes in the graph, and each node, starting with a root node, is linked to at most 2 other nodes. These are the child nodes, that would be the parent node. This is a binary tree structure. You'll see them if you go on and do more courses in this kind of stuff. So, for many, many algorithms, it's much more convenient to define the algorithm recursively than iteratively. Because all you have to do is design the algorithm so that it works for this node and calls itself for these nodes, and then you've solved the entire algorithm, basically. So, like for example, if I were to write an algorithm for a binary tree that was like searching for the number 4, I would write an algorithm that would say something like, is the current node's value 4? If yes, return true. If not, call this algorithm on both the left and the right node in sequence. So, how that would work through this one is as follows. Is this 4? No. Okay, do left node. Is this 4? No. Okay, do right node, or do left node. Is this 4? No. Okay. Since there are no nodes, it just does nothing. So we go back here. This guy's still working on this one, right? He calls his right node because he's got no response back, no dice from the left node, right? So, is 4 the value of this node? Yes. Return true, finish algorithm. That's a much more efficient way of going about the solution to that problem than any iterative solution that you might come up with. Though you could do the same thing with loops. It would become a lot of bookkeeping. And you have to, in order to do the same thing with loops that you're essentially doing with the system call stack here, you would have to keep a lot of variables just to keep track of where you are in the data structure, right? And like where the last branch that you didn't make was and stuff like that. Whereas with a recursive algorithm, it's like bing, bang, boom. I've defined it for one node, I get it for the rest for free. Make sense? Good. So, it is not a panacea, though. Panacea is a Greek word meaning a heal-all or a cure-all. Sometimes the structure of the problem means that recursion is probably going to be an inefficient solution to the problem. This is kind of like, again, in the same way that many different programming languages, in the same way that I'm trying to encourage you guys to think of programming languages as different tools in a toolkit that all operate on different, perhaps intersecting sets of problems, but never completely intersecting sets of problems. Think of loops and recursion in the same way. They can both solve all problems, but they're much better at some problems versus others. So we're going to see a problem here that recursion is not great at, for reasons that will be illustrated. This is the Fibonacci sequence. How many people have heard of the Fibonacci sequence? How many people have only heard of the Fibonacci sequence because of Dan Brown? There we go. All right. So, the Fibonacci sequence is a very famous sequence of numbers. Basically, you take each number, you take a series of numbers, you start with 1 and 1, and each number is the sum of the previous two. So the next 1 plus 1 is 2. 1 plus 2 is 3. 3 plus 5. 2 plus 3 is 5. 3 plus 5 is 8. 8 plus 5 is 13, etc., etc., etc. It turns out that the Fibonacci sequence has a bunch of really, really interesting properties, like a relationship to the golden ratio that I'm not going to get into here, but if you're interested, there's a very interesting video about pathfinding algorithms for bird-like objects on YouTube by a YouTuber named Sebastian Log, who goes into how you can create spirals using the Fibonacci sequence to do ray tracing to determine non-collision between bird-like objects in a space with geometries inside of it. But at any rate, it's cool. It's only like an 8-minute video. But anyway, so the Fibonacci sequence should be reasonable to come up with an implementation of this, right? You can see, hopefully, that it is structured very similarly to the factorial function, really. There we go. So, def fib m if n equals 0 or n equals 1, return 1. Else n is greater than 1. Return fib n minus 1 plus fib n minus 2. Save. And let's, just for the sake of interest, for I in range 10, print fib I. That's double R on the return. There we go. See if this compiles. Nope. Oh, no. Oh, yeah, it is. Thank you. There we go. So, Fibonacci sequence, which is mostly cut off here, so let me just move this over here. There. Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, etc., etc., etc. Good. Fine. Excellent. So let's imagine for a moment that we wanted to compute a slightly larger Fibonacci number. Let's print fib of 30 and comment out this stuff. Did you notice the delay? I'll do it again. Let's try again. Let's say 35. The delay is increasing. How about 40? We might be here for a while. So the thing that's going on here is essentially the problem. Well, okay, who wants to try to hypothesize what the problem is? Why is this so slow? Any ideas? Yeah.
Maybe like you see on the stack drawing here,
Hmm?
it's taking it for like it's using so much memory because it's n minus 1 and n minus 2 that it takes a while to do it all.
Yeah, that's like very close to the answer exactly the answer I wanted.
That's good.
Yeah. So any other ideas? Okay. So essentially, the problem is that in the definition here, we have 2 recursive calls to Fibonacci for every 1 recursive call that we make, or for every 1 call that we make. So every time we run through, basically, you can, like, the number of recursive calls that you actually need to calculate this function explodes, it's actually exponential on the number that you're trying to calculate, right? So that's why, you know, I can only increase it by 5, but it multiplied the amount of time it took to calculate that number by, you know, some large factor. Like it took like 2 minutes or something, didn't it? Something like that. We could actually time it in Unix at least. Here we go. So, so this is a problem, right? But let's dig into the structure a little bit and see what's going on. So, they want us to do the counting. Okay. So you can see, well, 2 minutes is maybe overstating it, 22 seconds, right? So let's modify the algorithm so that it counts how many times it's called fib. So counter is equal to 0. Global counter. This is the only time you'll ever see me use a global variable in class. Counter plus equals 1. Print that. Print number. Oh, jeez. Number of calls to fib equals, and then counter. So let's run this again. We'll see that it's going to be rather large. Almost. I almost got it. Anyway. So while that's running, we'll just keep talking about the slides.
Oh.
There we go. So the number of calls to the Fibonacci function, let's see, the 160,281. So a third of a billion calls to that function in order to calculate the Fibonacci number of, what was it, 40? 40, yeah. So that's a bit extreme, eh? One might say there's not a third of a billion numbers between 40 and 0, you know? That's perhaps the safest statement I've ever made in this class. So, obviously, we're doing a lot of recalculating, and we don't necessarily need to do it. So, this is what this looks like, right? If you were to break this down in terms of a tree structure, yeah, just going with 4 for the moment. So if you were to calculate fib 4, you need fib 3 and fib 2. Fib 2 needs fib 1 and fib 0. Fib 3 needs fib 2 and fib 1. Fib 2 needs fib 1 and fib 0. See that fib 1 has been calculated 3 times here, fib 0 twice, fib 2 twice. Now, if you imagine this whole graph being multiplied every time fib 4 needs to be calculated, and if you imagine every instance of fib 6 needing fib 4 and fib 5, etc., you can see how this blows up very, very, very quickly, right? Extremely quickly. So, so the number, like if you were to run this for some low numbers, right? Fib 4 only needs 9. Fib 6 is 25. Fib 8, 67. Fib 10, 177. You should be able to recognize exponential growth when you see it. So we already talked about infinite recursion. So with this algorithm, what would be one way you could make it go into infinite recursion? Anybody?
I don't think you can do this with negative numbers.
Yep, negative numbers would make it throw up once again. You can also modify the algorithm. Like with this one, it's kind of interesting, right? Because like you're not just dealing with an n-1 case, but an n-1 and an n-2. So if you contrived it somehow that you know, if you had like you know, 0, -1, -2, 1, 2, 3. Like if you contrived it somehow that the thing basically jumped here, here, etc., and missed the base case, then it would also go into infinite recursion despite starting on the right side of things, right? So that's also a thing that you have to be aware of when you're working with things of this nature. Good. So we have this problem where clearly we are repeating calculations that we don't need to. Does anybody have any kind of idea how we might be able to get around this problem? Yes?
You create a memory bank. For example, once you calculate fib 1, you put it into memory bank. And if you calculate fib 2, you might put it in memory bank, and then it calls upon fib 2, you already have the number ready.
Precisely correct, yes. So what we need to do is we need to set up some memory to store the intermediate results. Now we need to do this in a particular manner because, you know, this is recursion and function calls. So, you know, essentially, we're going to use a strategy called memoization, but it's also it's like a it's basically the same idea as caching. Caching means storing intermediate results so that they can be pulled out and not have to be recalculated. So, I think I can finish that in the next 5 minutes. So, so first, our memo is going to be a dictionary. So, dictionary. D. So rather than just directly calling fib n-1 and fib n-2, let's make that so that these values must be found in the dictionary. And if they don't exist in the dictionary before we get to this line, we'll add them. That's essentially the strategy. So, we now must perform a check to make sure they're in the dictionary. Fortunately, this is very easy in Python. If n-1 in D, then do something. Actually, not in would be better, because we want to add it to the dictionary if it's not in the dictionary already. So, how do we add stuff to a dictionary? We simply use assignment. What is this equal to? Fib n-1. What do we do to get this next one? Very simple. Copy the whole thing. Replace all the ones for twos. That is a traditional programmer's trick. Copy paste with small modifications. One more thing that we need to modify, we need to remember to pass the dictionary to the recursive invocations. So, let's see how this works. Yes, okay. So it's missing a positional argument, so rather than actually give it what it wants, I'm going to make an empty dictionary the default value of this dictionary. So, note, first of all, previously this took half a minute. It now takes 0.37 seconds, which is not much more, that's not much longer than it would take to calculate anything or run any program. Number of calls to fib, 41. So we have accomplished our goal. Any questions about that?
Picture?
Yeah, so, yeah. It's also all being recorded, so. Yes?
Sorry, why is the global counter?
Why is the counter there?
Yeah, the global counter.
Oh, so the global, so because these are function calls, if we were to bind a variable counting the number of function executions to the local space of the function, it just, you'd only ever have the local instance of that function, right? We would have to, put it in as an argument, which in theory we could do, but, I don't know, it's a way of keeping track of how many times the function is called across all function calls easily and quickly, you know? Perhaps not the best way of going about it, but that's the way we did it. Any other questions? Good. So, now come on, we got 2 minutes left. So, when we measure runtime, when we measure things, right, generally speaking, there are two main metrics that we're concerned with. One is the amount of time it takes to run the program. The other is the amount of memory that it consumes. Now, sometimes, if you're lucky, you can have a nonlinear trade-off between the two. So what we have done here is we have exchanged a heck of a runtime for a very small amount of memory. So that was a very good deal. But these deals, like, you can imagine if you were going in the reverse direction for this particular problem, that would not be a good deal. So it's your business as the software designer to make sure that the deals you're making between execution and memory are good ones. Caching is generally a good strategy, though. Yeah, okay, fine. See you guys on Wednesday.